let's talk about the speed of a wave. Now, in general, the speed of any wave, any physical wave, and I'm skipping past the electromagnetic wave. Electromagnetic waves, it's a different animal. But in terms of any of the other physical waves, the basic generic formula is the speed of a wave is the square root of what I'm calling the affecting factor over the inertial factor. An affecting factor is if I move one molecule, whatever the medium is, if I move one molecule, how well does that affect the molecule next to it? So if I'm talking about a string, or let's take the rubber band. If I take a rubber band, if I pull here, how easily is that affecting the piece of rubber band that I'm not touching that's right next to it? And how well does that one? So that is what I'm talking about, the affecting factor. If I'm talking about a bulk modulus, so if I'm talking about three-dimensional, if I'm talking about sound moving through a solid, something called the bulk modulus, that if I hit one part of I'm picturing railroads right now. If I hit one part of the railroad, how well does that affect the thing next to it? And the inertial factor is how easy is it to get something to move? The greater the inertia, the harder it is to get it to move. And so I've got these two competing factors. So if I take a solid, if I move one part of the solid, the other part of the solid moves really well. For instance, if I'm moving a book across the desk, all I have to do is pretty much touch one part of the book, and the next part of the book moves with it. Water, not so much. If I push on water in one spot, all the water doesn't move. Eventually, it gets there. It depends on how much water there is. And with gases, if I do this, is the person in the room next to me over there, is that person affected? Does that person feel it? Probably not. And so these are the affecting factors. But on the other flip side of it, the inertial factor, with solids, you got more mass, you got more inertia. And so the inertial factors lessen as you move towards gases. And so you got these two competing effects. Now, if I'm talking one-dimensional motion here, so I'm talking something traveling, let's take the rubber band, starting out with just the rubber band. If I push on this right here, the affecting factor, well, in essence, it's the tension. That's what tension is. It's a pulling of one part of the object onto another. So if I pull here, well, the tension, the force that's pulling on the next part of the rubber band here, and then here, and then here, and then here, it's just the tension in the rubber band. And the inertial factor, well, generally density comes into it. And so for one-dimensional physical wave motion, the speed is equal to the square root of the tension divided by what's called the linear density. So linear density is just the mass divided by the length. That's just an average linear density. So the greater the mass, if I have a lot of mass and a short length, well, that's a huge amount of inertia. If I've got the same amount of mass and a much longer length, well, that's less. So let's go back to the rubber band here and see how this affects anything. So I have a rubber band like this, and there's a certain sound. Actually, I'm going to do it off screen to start out with. We'll get it down like this. All right. So I've got a certain amount of tension in the string, and there's a certain sound there. As I make it longer, now let's analyze this. As I am stretching it out, I'm increasing the tension. My speed, so this gets bigger. As the speed gets bigger, as the tension gets bigger, the speed gets bigger. So I increase the tension, speed increases. So what is happening there is I now have a faster wave traveling through it. Now the wavelength is not really changing because the wavelength depends upon my plucking. So if my wavelength is pretty much staying the same and my speed increases, let's go back. Let's think back to a couple of videos ago. And don't happen to have that piece of paper with me, but I'm going to rewrite down that the speed is equal to the frequency times the wavelength. So as my speed increases, my frequency increases. Higher frequency means a higher pitch, means you're hearing a higher sound. And that's exactly what's happening here. That we start out with, but as I stretch the thing, so as I stretch it, it gets bigger. Sorry, the frequency gets bigger, or I mean the higher frequency, higher pitch. Now, let me take this one step further. Since the speed is equal to the tension over the linear density, and the linear density is just the mass over the length. So all I did was make a substitution here. So it's the tension over the mass over the length, and then I'm dividing by a fraction, same as multiplying by the reciprocal. So it's the tension times the length over the mass. So if I had some sort of string where the mass got smaller per length, the mass per length got smaller, well, the speed should increase. Well, does such a thing exist? Well, yes. The whip. Notice that we can treat it as a line. Yes, it is a three-dimensional object, but we can treat it as a line without a whole lot of loss here. That there is a certain amount of mass in this amount of length here. But as I go for the same length, now it's getting skinnier, which means less mass. And skinnier, and skinnier. And as I go, it gets smaller. The linear density gets smaller and smaller, which means the speed starts increasing. So I put a certain amount of tension into the whip. I put a certain amount of tension into the whip by just going up and back. As I do that, the wave starts traveling down. The linear density starts dropping until it gets smaller and smaller, and then the linear density drops even. Suddenly there's a big boost there, and then when we get to here, there's a huge boost. And so now this wave is traveling down the string, and the wave in the string only actually has to be traveling at half of the speed of sound. Because when the wave gets to here, this thing is suddenly going to whip up at the very end. And when that whips up, basically as the wave changes direction, the speed of the tip here is the thing that breaks the sound barrier, and that's the crack that you get. So I'm doing this in the room, so we'll find out if I actually hurt myself or not. Let's see how well I can do this. All right, doing this in a small office is not a good idea. Don't try that one at home. If I remember, I will do this in the classroom. I've done this in the classroom. It's better done outside, but you know what? What's the point of doing physics unless you can't do stupid things? So anyway, that speed of a wave has become very important when we start dealing with the vibrating string lab.